but it's not always true. So anybody remember what this pattern is called right there? What's another way to say minus? Difference. That's the difference of? It is the difference of squares. What's the first factorization, Umi?
So it would be s squared minus 1 times s squared plus 1.
Yeah, s squared minus 1 times s squared plus 1. And then we have another difference of squares in there, so what does it continue to be?
Yeah, so s squared minus 1 would become s minus 1 times s plus 1.
And then you still have that s squared plus 1. So what's the breakup you would have to do? Can someone else set it up for me? Like, what are we searching for now? What's the breakup? Hannah?
A over
Yep.
s plus 1
Yep.
plus b over s minus 1
Uh-huh.
c over s squared.
So this is the challenging part. And just, hold on, and just because it's not on the AP test doesn't mean it's not good to actually see where this is going. What's the power of the denominator on that one? 2. So you have to put a general term that represents 1 power less. So it's going to be cx plus what? D. So there's actually 4. The reason they limit you specifically to single power linear terms is because when you start introducing higher powers, the algebra gets really annoying. Is it already annoying sometimes? Yeah, the logic already gets annoying. And again, it's an AP calculus test, not an algebra test. You need to know some algebra. You need to be able to perform it. But 90% of your time should not be spent decoding a 4x4 linear system. In this case, though, you know that all the way to the left, well, you can say all the way to here, this is equal to these 3. So what do we multiply by to clean it up, Matt?
We multiply that.
Yeah, so we have A times what? S minus 1 times s squared plus 1 plus b times s squared plus 1 plus what? Times. And do you remember how there were 2 methods? There was like the full logical method that we used, but then there was the magic number method that we talked about. Nate, you were a fan of that magic number method. Why was that magic number method really nice? Yeah, now let's just look at this one. This one, the only thing that changed is that cx plus d, but would you look forward to doing all that algebra with this one? Just, you can say no. It's totally fine. So what's one of the magic numbers that we could use? What's one number we can plug in for s that folds a lot of things away? 1. Yeah, so if we say s is 1, we end up with 2 is equal to, what happens to the first term? It goes away, doesn't it? Because you plug in 1 right there. 1 minus 1 is 0. It's gone. But then you end up with b times 2 times 2. And what happens to that third term? It disappears as well. So can we directly find b? What's b equal to? 1 over 2. Yeah, that's nice. What's another magic number we could use? What's the other nice magic number we could use? -1. And what happens when we do that one? We end up with 2 is equal to a times -2 times 2. So what does a equal? Hey, we had a and b. Now here's where it gets more fun, and this is actually really kind of cool. This is on this question, someone came up with this in the last class. At this point, you kind of run out of magic numbers. You do, but guess what? You don't. There's a number you can plug in that gets rid of a and b, but doesn't get rid of cx plus d. Does anybody know what that number is? What are the only factors that are common to the a block and b block? S squared plus 1. So guess what our magic number is going to be? S is going to be equal to I. And why are you really, really hesitant to substitute I in? Oh, come on. It's like the coolest number ever. We already did this. E to the pi I plus 1 is equal to 0. That's the coolest. Yes, it is. Yes, it is. Here, but give me another reason why you're reticent. Why are you hesitant? Why? You might be hesitant because you're getting excited. Why?
Because if you I squared is equal to -1.
Yeah, so here's the thing. If you plug these in, look what happens. What happens to the first 2 terms? They go away. And you might be hesitant because you're like, okay, we still have cx plus d, and then we have I plus 1 times I minus 1. We just don't want to have an I left over. But what happens when you multiply that out? You end up with cx plus d. You end up with I squared minus 1, minus I plus I minus 1. What happens to the i's in the middle? What happens to the i's in the middle? They cancel. Do these things that we're not a fan of go away? Yeah, and what is I squared? So you end up with 2 is equal to cx plus d times what? Negative 2. What can you divide both sides by? So you end up with negative 1 is equal to cx plus d. And you're like, oh man, I have one equation and 2 things. Oh, well, wait a minute. Does that tell you everything you need to know right there? Are there any x's on the other side? So what does c have to be, Umi? 0. C gets to be 0, but then what does that mean D is?
Why is it X and not S?
Oh, did I just stop using S? Why is it X and not S?
Yeah, why is C multiplied by S?
Because look at what we set up here, remember? Oh, cool. Why did I suddenly start using X instead of S? No good reason. no good reason. None at all.
Should it be C times I plus
C times I. Oh, excuse me. No, it's you use C. You're breaking. So you're asking. Let me pause this here. Polynomial long division. I was not the one that taught you it, but when I teach it, there's only one phrase I like to impart to people: leading over leading. Leading over leading. What's the leading term underneath that little division sign right there, or large division sign? X to the 4th. And what's the other leading term? What's x to the 4th over x cubed? What do you do with that x? Yay! And after you do that in division, it follows the same pattern you had before. What do you do with that x? Multiply! Yay! You take it there and you multiply it by all these pieces and you get x to the 4th plus what? 12x cubed plus 11x squared. Yeah, exactly. And do you remember what's that next step? And it just follows division. What do you do next? You subtract. Exactly. When you subtract, oh, does the first term go away? Yeah, that's kind of nice. Those go away. And should they go away? Yeah, the whole point of doing that division is you're getting rid of that first one. If they don't, then something went wrong. What's also nice is what happens to the next term? It also goes away. That's kind of a nice thing. Leaving you with just what? 4x squared. What's the power of this term? 2. What's the power of this term?
3.
What does that mean you do at this point? Stop. You stop. If the power is less than what you are throwing into it, you stop. So are there other things that we drop down at this point? What is that whole thing called down here? Yeah, that's the remainder. That's the remainder. We have now shown that this thing, this big one right here, is equal to x plus 4x squared plus 25x plus 11 all over what? Plus 11x. Exactly. We have now shown that those two things are equal. What did they give you? What's the last piece of information, the ABC thing? What does that help you with? It helps you with the factoring. They effectively have given you the factoring. So they're telling you that this thing right here is going to be equal to x plus a over, what was it? A over x plus b over x plus 1 plus c over x plus 11. We are now at the point of doing the same type of work we just did. The same type of work we just did. So what's our first step? We're not going to finish this one right now, but we're at the point that we were at the beginning of the last problem. What would we multiply both sides by at this point? The denominator. And you're left with 4x squared plus 25x plus 11 is equal to everything on the other side. Now, are there nice magic numbers on this one? Yeah, what are the 3 magic numbers on this one? 0, -1, and -11. You have 3 magic numbers and A, B, and C to solve for. So do they all come out? They do. They come out nicely. Like with any equation, what's the best thing you can do? Let's say you were totally lost and you had no idea how to graph this or to describe the motion of this particle. What's the one thing you could always do? You can make a graph. But if you're going to make a graph, you need points to put on the graph. And what's a great way to write a table? Right. So let's make a table where we have time, x, and y. If t is 0, what is our x value going to be?
1.
1. So what's our y value going to be? 0. If our t value, now we have to be careful about our t values, right? Should we choose a t value? Hey, bless you. 0.1? No, we should probably choose values that are on the unit circle, right? So we have pi over 4, maybe? Is that okay? So what's the x value going to be? Root 2 over 2, maybe? And then what? Root 2 over 2. And what's the next trig value, maybe? Pi over... Let's do pi over 2. Let's do pi over 2. What's pi over 2 going to be? 0 and 1. So if we were to put this information together, what does this start looking like? With radius centered at the going in which direction? Counterclockwise. So we now have a circle, and it looks like it's starting here at 1, 1, and it's going around. I missed the dots. That's great. But it's going counterclockwise. Does it end up rotating on itself? It does. Does it end up going back on itself? Absolutely. But the point is, you have a circle of radius 1 centered at the origin going in a counterclockwise direction. If you're ever lost on a parametric equation, graph a few points. It helps. Just graph a couple points. How many points do you need to know what direction this is rotating in? Just 2. You just need 2. When we get to more involved, crazy parametric equations, can parametric equations sometimes double back on themselves and like do weird things? Absolutely. With sine and cosine, are we pretty good about going in one direction? Absolutely.